Okay, in this problem, we're going to look at what's called the half-life. It says here that we're going to calculate the change in concentration after a whole number of half-lives of a first-order reaction. So I'm going to point out that this is a very specific type of problem in a couple of ways. One is that it's a whole number of half-lives. Any problem that doesn't use a whole number of half-lives would have to be dealt with differently. But if it specifically says a whole number of half-lives, then we can use this approach. The second point I want to make is that it also depends on the order of the reaction. If it's a second order or zero order, we would use a different equation. We would use a different approach, not a different approach, but a different specific equation. This, what I'm going to show you here, only works for first order, okay? So when we read the question, it says, the rate at which a certain drug is eliminated by the body follows first order kinetics with a half-life of 20 minutes. Suppose in a particular patient, the concentration of this drug in the bloodstream immediately after injection is 1.9 micrograms per milliliter. What will the concentration be 100 minutes later? Round your answer to 2 significant digits. Okay. So I'll bring up the whiteboard here and we'll take a look at it. There we go. Okay. So it's first order. And what we're told is that the half-life is 20 minutes. Okay. Now, briefly, what is the half-life? Well, the half-life is the amount of time it takes for the concentration of a substance to decrease by 50%, to decrease by 50%, to go down by 50%. So in other words, we'll have 50% of it left. Okay, so what I'm going to do is I'm going to make a little table. So there's time in minutes, and then I'm going to do concentration. And the units are micrograms per milliliter. Okay, and what we're told is that the initial concentration of the drug in the bloodstream immediately after injection is 1.9 micrograms, 1.9 micrograms per milliliter. That's at time equals 0. Okay, so at the beginning, the way we would say that mathematically is we would say time equals 0. Then after 20 minutes, we will decrease the concentration by 50%. In other words, we'll just go down to 1/2. So 1/2 of 1.9. Now 1/2 of 1.9 is 0.95 micrograms per milliliter. Then we go another half-life. Now the half-life is 20 minutes. So we go another 20, and that would give us 40 minutes. And then we're just going to take a half of 0.95. So you just take a half of what you're left with for the previous one. So half of that would be 0.475. Okay, just go down by half each time. Another 20 minutes would give us 60. So each unit of half-life, 20 minutes. So a half of 0.475 would be 0.2375. I'm not worrying about significant figures yet. Another 20 minutes would be 80. Half of 0.2375. Well, that would be 0.11875. Okay, get the idea? Let's go up another 20. 100 minutes. Half of 0.11875. And that gives us 0.059375. We only need 2 digits past the decimal. Well, not actually, be careful. We need 2 significant figures or 2 significant digits. A leading 0 is not significant, so that one doesn't count here. So we would start at the 5. So 1, 2, 5, 9. 3 is less than 5, so we can just truncate it. So you get 0.059. Of course, the units are micrograms per milliliter. Okay, and there's our answer. After 100 minutes, we would have, roughly, what is this? 50, 25, 12 and a half, 6, about 3% of what we originally had. You just go down by halves. Again, that only works, this method, it's a very simple method. It only works for first order, and it only works also for exact multiples of the half-life. So if I'd asked for how much would be left at 95 minutes or 89 minutes, to get an accurate answer, you wouldn't use this approach. You would have to use the integrated rate law for first order kinetics, which would work, but for this particular problem, we're not doing that.